This is the first part of the recorded lectures for Chapter 2 on chemistry, and I wanted to give you a little bit of information on why we study chemistry in anatomy and physiology. There are a couple of reasons. Well, first and foremost, chemistry is our body is made of cells, and our cells are made of chemicals, compounds and molecules. And those molecules and compounds are composed of atoms. So we have to have a certain understanding just to understand anatomy and physiology as we move forward. But also, this information is found on the TEAS test. And so we always teach this as a review chapter to make sure that this information is covered. Some students are going to have had more chemistry than others. There are actually going to be some of you that have never had a chemistry class at all, never even took chemistry in high school. And so this is kind of, we try to do this chapter to review basic chemistry and then cover the major molecules, organic chemistry, organic molecules that are found that compose the human body. So these are the learning outcomes for the chapter. We will first talk about atoms and then the particles that make up atoms, the structure of atoms. And then we will go on to 2.2 and we will talk about how atoms combine to form molecules and compounds. And then we will move to 2.3. The 3 types of chemical reactions. One will be the reactions that break down larger molecules, and another will be the reactions that build molecules, and then there will be reactions that don't break down or build anything. They just rearrange atoms. There's just more of a rearrangement type reactions. Then we will talk about enzymes. In 2.5, you need to know the difference between organic and inorganic compounds. I'll go ahead and tell you the biggest thing with organic compounds is that they consist of 2 elements, carbon and hydrogen. They must have both carbon and hydrogen to be considered organic compounds, carbon and hydrogen. All right, and then we will talk about the chemical properties of water. The pH scale, which is the measurement of the degree of how strong of an acid or how strong of a base that something is. We will have the next learning outcome is acids and bases, and then salts, which are neutral. 2.9 through 2.12 are going to be learning outcomes about the major macromolecules that compose our bodies. And they're going to be carbohydrates, lipids, proteins, and nucleic acids. And then we will have a section on ATP, high energy compounds like ATP. ATP, or adenosine triphosphate, is the molecule that our cells use for energy. And then the relationship between chemicals and cells. The definition of chemistry is the study of matter and its interactions. Matter is anything that takes up space, or another way to say that is it has a volume. And we usually measure volume in milliliters or liters. And also matter has mass, and we usually measure mass in grams. For small amounts, it would be milligrams, and then for large amounts, it would be kilograms. But the base unit is grams. And mass is the amount of matter an object contains. The chemicals that we're going to study are called elements. The elements are all listed on the periodic table, but you are not going to have to know the entire periodic table, so you can breathe a sigh of relief because you're only going to have to know a few of those elements. And I'll be more detailed when I post your study guide for Chapter 2. I will post the elements that you actually need to know for anatomy and physiology. The most important are these 6, and they form the mnemonic device, CHNOPS. It's a little word that every letter stands for the symbol for each of these elements. So the C stands for carbon, the H stands for hydrogen, the N stands for nitrogen, the O stands for oxygen, P is phosphorus, and S is sulfur. So these are elements you need to know the symbol and the word. Okay, the symbol is just the letter that stands for that element. Now we're going to talk about atoms, which are the smallest units of matter. An atom is the smallest piece of an element. You can't break it down into a smaller piece. So for example, what we have over here in the bottom right, figure 2-1, is the element helium. It's the second element on the periodic table. And there's not, by the way, there's not a periodic table in this slideshow because you really don't need one. But I will give you a few examples of some of the elements on the periodic table just so that I can talk to you about some things. So helium on the periodic table would look like this. There would be a box, and it would be a much more uniform box than the one I'm drawing, but I'm doing the best I can. So there would be a box, and then you would see the symbol for helium, which is He. Since H stands for hydrogen, we have to have something different than an H, than just an H. And then you would have two numbers. There would be a mass number, which is the larger, the larger of the two numbers. Let me fix that. Okay. All right, I'm going to try to fix this. Here's our box. Helium stayed, so then we have a 4, that's our mass number, and then a 2 is our atomic number. So I'll tell you what those numbers tell you about helium. So first of all, let's go back and talk about atoms. Atoms are composed of subatomic particles, protons. Okay, for each of these subatomic particles, make sure that you know the charge and the location. So protons have a positive charge. They're located in the nucleus of the atom. So helium has 2 protons. And another thing that tells us that helium has 2 protons is the atomic number 2 that you see in the box on the periodic table. So that number 2 is the atomic number, and it tells us that helium has 2 protons. Okay? Neutrons have a neutral charge. That means they're uncharged, and they are located also in the nucleus. And helium has 2 neutrons, but the way that you get the number of neutrons is not, they don't always equal the number of protons. What you have to do is take the mass number, which for helium, the mass number is 4, and subtract the atomic number 2. So 4 take away 2 is also 2. So the number of neutrons is going to be 2 because it is the mass number, subtract the atomic number. 4 take away 2 is 2. Then the electrons have a negative charge, and they are located outside the nucleus in electron shells. And the number of electrons are going to always equal the number of protons because the negative charges and the positive charges have to be equal to each other so that there's an overall neutral charge on the atom. And this is just a picture explaining that electrons don't reside in the nucleus. They reside outside the nucleus in electron shells. And then in the atomic number, again, is the number of protons. Any element is always going to have the same atomic number. So let's look at carbon. Let's do that again. Okay, let's look at the symbol for carbon on the periodic table. Sorry about that. Okay, carbon, remember the symbol is a C. All right, the mass number is 12 point something. We're just going to round it to 12. And the atomic number is a 6. Okay, so what that tells us is that carbon has, the 6 tells us that carbon has 6 protons. I don't want to leave it like that. I'm sorry it keeps doing it. Okay. All right, so the 6 tells us that carbon has 6 protons. And we know that the number of protons is going to equal the number of electrons. So carbon also has 6 electrons. And the way that we get the number of neutrons is we subtract the mass number, take away the atomic number. So the number of neutrons is 12 take away 6, which happens to also equal 6. Okay. Six. Ugh. I just don't want to leave it like that. Okay, I'm going to try this one more time, and then I won't do a lot of drawing after this. Okay. Ugh. 6 neutrons, because 12 take away 6 equals 6. There are some cases where the number of neutrons does not equal to the number of protons and electrons. All right, I'm going to just try this one more time so it doesn't stay. All right, now all I have to do is get an N in there. There. Okay, try not to draw anymore after this. Okay, so isotopes are forms of elements that have different numbers of neutrons. In other words, their atomic numbers are the same, but their numbers of neutrons are different. So, for example, we just talked about carbon. Carbon can either have 6 neutrons, 7, or 8 neutrons. And that changes the mass number as well, because the mass number is the total of the protons and the neutrons in the nucleus of the atom. So if we've got, I was just looking to see if they had an example on the next slide, but they don't. So if we've got carbon 12, for example, the mass number is 12. I'll just draw it like this, carbon 12. Okay, that means the mass number is 12, and when we go back to this slide, remember we calculated 12 take away 6, that gave us 6 neutrons. Well, there's also an isotope of carbon called carbon-13. Okay. Okay, there's an isotope of carbon called carbon-13. So if we go back to the previous slide, this time there would be a 13 here for the mass number. So when we do the protons, we still use the atomic number. There's still 6 protons and 6 electrons in the carbon-13 isotope. But now we're doing 13 take away 6 to get the number of neutrons. So the difference would be that carbon-13 would actually have 13 take away 6 is 7 neutrons. And there's an isotope of carbon called carbon-14 that has 8 neutrons. So the takeaway here is that isotopes are going to have different numbers of neutrons, and therefore they're going to have different mass numbers, okay? And some of the isotopes are radioactive, and they can be used in diagnostic imaging. Iodine, for example, a radioactive form of iodine is used in doing iodine scans of the thyroid. This is just telling you that the atomic weight sometimes in the periodic table is a decimal, but you round it to get the atomic mass or the mass number.